Dear students, Namaste and welcome back to a new mathematics session. In the previous session, we were discussing about the conditional probability and we have solved some questions from exercise 13.1. Hope it was clear for you all. In today's session, we shall discuss the remaining problems from exercise 13.1. Let's move on to the topic. Move on to question number 14. The question is, given that the two numbers appearing on throwing two dice are different, find the probability of the event the sum of the numbers on the dice is 4. Given condition is two numbers appearing on two dice throwing time are different. You have to find out the probability of the sum of the numbers on the dice is 4. When two dice are thrown, the sample space looks like this: 1 1, 1 2, 1 3, 1 4, 1 5, 1 6. Means the first die appears on 1 and the second shows 1. First one shows 1, second one shows 2, and it goes up to 6. There are 36 elements. Let's take the event E. The sum of the numbers is 4. That is what it is given to us. The sum of the numbers is 4. Means the possible outcomes of E are, you can look this sample space and you can write down 1 3, 3 1 and 2 2. So if you write the sample space, it will be easy for us to write down the events of E. If you are not writing the sample space and only the number of elements in the sample space if you write, you should have the common sense to write these elements. So whichever way is convenient for you, you can just choose. Either you can write the sample space and from the sample space you can write the elements of E, or else you can write simply the number of elements of sample space, because we want the number of elements for finding the probability, and you should have to use your sense to find out the elements of E. Means the sum of the elements, if you get 4, those are favorable outcomes. Means 1 3, 3 1 and 2 2. F means numbers are different. That is what the given condition. Two numbers appearing on throwing two dice are different. That is our condition. So we have taken as F. So F, the possible outcomes of F are, from here the same elements 1 1, 2 2, 3 3, 4 4, 5 5 and 6 6 can be removed. So those elements I have removed, and the balance it shows the elements of F. Then P of F we can write. There are 6 elements we have removed. So total 36 elements. From there 6 we have removed. So the possible outcomes of F is 30 divided by the total number of elements of the sample space, that is 36. From here we will get 36 elements. Then E intersection F, when we calculate, E is this one, F is this one. Surely 1 3 and 3 1 are the intersection F, E intersection F elements. So 2 2 will not be included because 2 2 is removed from here. So because they are the same elements. So E intersection F means 1 3 and 3 1 are the intersection elements. Then P of E intersection F is, there are only 2 elements. So 2 divided by total number of elements in the sample space is 36. So 2 divided by 36. So P of E given F is equal to P of E intersection F by P of F. This is the formula, and when we substitute, P of E intersection F is 2 by 36 divided by total number of, probability of P of F is 30 by 36. 36 and 36 can be cancelled, and 2 divided by 30. 2 divided by 30, when you cancel 2, we will get as 1 divided by 15. So the required probability is 1 divided by 15. Next we shall discuss question number 15. The question is, consider the experiment of throwing a die. If a multiple of 3 comes up, throw the die again, and if any other number comes, toss a coin. Find the probability of the event the coin shows a tail, given that at least one die shows a 3. Here let's go through the question again. Consider the experiment of throwing a die. We are asked to throw a die and we have to observe the result. If a die is thrown, we are getting the possible outcomes as 1, 2, 3, 4, 5 and 6. There are 6 possible outcomes. Then if a multiple of 3 comes up, we have 1 to 6 numbers, and if a multiple of 6 comes, means we should get either 3 or 6. 3 and 6 are the multiples of 6 within these numbers 1 to 6. If 3 or 6 comes up, we will throw the die again. The same process will continue. We will throw the die again because first also we have thrown the die, and again if we get 3 or 6, we will throw the die again. And if any other number comes, means 1, 2, 4 and 5 comes, means we will toss a coin. So find the conditional probability of the event. The coin shows a tail given that at least one die shows a 3. So let's summarize the question. We will be throwing a die first and we will observe the outcome. If 3 or 6 comes, means we will throw the die again. If 1, 2, 4 or 5 comes, means we will toss a coin. So we are asked to find out this conditional probability. So the sample space when we write, first we are getting 1. So 1 is not a multiple of 3. So we will go for tossing a coin. Head will get or 1 tail will come. When the die shows 2, 2 is also not a multiple of 3. So we will toss the coin. We will get the chances 2h and 2t. Then when 3 comes, 3 is a multiple of 3. So we will toss the coin, we will toss the die again. So there are 6 possibilities again. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5 and 3, 6. Then if the die shows 4, 4 is not a multiple of 3. Again we will toss the coin. So head and tail are the possibilities 4h and 4t. Then if the die shows 5, 5 is not a multiple of 6. Then again we will toss the coin. 2 possible outcomes, that is h and t. 5h and 5t are the outcomes. Then finally if the die shows 6, it is a multiple of 3. We will toss the die again. So the possible outcomes are again 1, 2, 3, 4, 5, 6. That is 6, 1, 6, 2, 6, 3, 6, 4, 6, 5 and 6, 6. So this is the sample space. Then let A be the event that the coin shows a tail and B be the event that at least one die shows 3. According to our given question, the conditions are written. A means the coin shows a tail and B means the event that at least one die shows a 3. So here A and B I have taken. If you want to take E and F, you can proceed. It's not a problem. Then A we can write. A be the event that the coin shows a tail. From here the tail shows. Which are the outcomes which shows the tail that we have to take. That means here tail is there 1t. Then here there is a tail 2t. The next there is 4t and there is 5t. So these are the possible outcomes 1t, 2t, 4t and 5t. Next is B. B is at least one die shows a 3. At least one die shows a 3 means 1, 3 or more than 1. 2, 3 is also no problem. So 1, 3 means here there is 3, 1. Then 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. And here the second row when comes there is only 6, 3. It shows 3. So these are the outcomes. That is 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6 and 6, 3. Then let's take A intersection B. A intersection B taking time. It is quite clear that there is no common element because in the first set A there is tail is there. In the second set there is no tail, only the numbers are there. So there is no common element. So A intersection B is 5. Then P of A intersection B, surely it is 0 because number of elements of A intersection B is 5, 0. So P of A intersection B is 0. So since the numerator we have got 0, no need to proceed because anyway we will get the final answer as 0 because P of A given B is P of A intersection B divided by P of B. So A intersection B, P of A intersection B we have got 0. So we can just stop the calculation here. So probability of the event that the coin shows a tail given that at least one die shows 3 is given by P of A given B. That is equal to P of A given B is equal to P of A intersection B by P of B. And we have not calculated P of B because P of A intersection B we know it is 0. So 0 divided by P of B, that is equal to 0. Move on to question number 16. It is a multiple choice question. If P of A is equal to 1 by 2, P of B is equal to 0, then P of A given B is, there are 4 options given to you. First option 0, second option 1 by 2, third option not defined, and fourth option is 1. So here given P of A is 1 by 2 and P of B is equal to 0. These are the probabilities given to us, and P of A given B we have to calculate. So P of A given B is equal to P of A intersection B divided by P of B. Here P of A intersection B divided by, we are not having the value of P of A intersection B. So let it be same. P of B is given to us, that is 0. So P of A intersection by A intersection B by 0. Division by 0 is not defined. So P of A given B is not defined. Here not defined one is option C. So option C is the correct one. Next we shall discuss question number 17. The question is, if A and B are even such that P of A given B is equal to P of B given A, then first one, A is a subset of B but A not equal to B. Second option, A equal to B. Third option, A intersection B is equal to 5. And fourth option, P of A is equal to P of B. So it is given to us the condition P of A given B is equal to P of B given A. So let's write the given condition. Then P of A given B means P of A intersection B by P of B. The formula P of B given A is P of A intersection by B by P of A. So P of A intersection B is common on both the numerators, cancelled. That is 1 divided by P of A is equal to 1 divided by P of B. Right side we are writing first. When you take the reciprocals, we will get P of A is equal to P of B. So the option D is correct. Next we shall discuss the next concept, that is multiplication theorem on probability. We have already learned that the conditional probability of event E given F has occurred is denoted by P of E given F and is given by the formula P of E given F is equal to P of E intersection F divided by P of F. This is the formula what we have learned so far. P of E given F is equal to P of E intersection F divided by P of F. So when we cross multiply it, P of E intersection F into 1. So P of E intersection F is equal to, this will go here, that is P of F into P of E given F. Let's take it as equation number 1. Next is P of F given E. P of F given E formula is P of F intersection E divided by P of E, provided P of E not equal to 0. Same like before, just go for the cross multiplication, that is P of F intersection E. P of F is F intersection E and P of E intersection F, both are same. So we can write it as this one, P of E intersection F is equal to P of E into P of F given E. Please note P of F intersection E and P of E intersection F are same. That's why here instead of P of F intersection E, we are writing P of E intersection F. So P of E intersection F is equal to P of E into P of F given E. That is equation number 2. When we combine equation number 1 and 2, left sides are equal. Here also P of E intersection F, here also P of E intersection F. Right side is P of F into P of E given F, here P of E into P of F given E. When we combine these two equations, we can write the statement as P of E intersection F is equal to P of F into P of E given F equal to P of E into P of F given E. So all these two equations we have combined. P of E intersection F is equal to P of E into P of F given E equal to P of F into P of E given F, provided P of E and P of F should not be 0. So this is known as the multiplication rule of probability. So multiplication rule of probability is P of E intersection F is equal to P of E into P of F given E, or P of E intersection F is equal to P of F into P of E given F. Next, we shall discuss about independent events. Let's take an example. Consider the experiment of drawing a card from a deck of 52 playing cards. So we are just considering a deck of cards, that is 52 cards are there, and each elementary events are assumed to be equally likely. Means all cards drawing, means whatever cards we are taking from a particular deck of cards, all are having equally likely chance, means equal probability. If E and F denote the events, the card drawn is a spade. E means we are drawing a card spade, and F means the card drawn is an ace. So let's find out P of E and P of F. So P of E means the card drawn is a spade. As we know that there are 13 spades in a deck of cards. So 13 divided by 52. Total number of cards in a deck of cards are 52. So 13 by 52, when we cancel 1 by 4. Next we will go for calculating P of F. P of F is we are choosing a card that is ace. So there are 4 ace are there in a deck of cards. So 4 divided by 52, that is 1 by 3, 13 is the probability. Next, E and F is the event. The card drawn is an ace of spades. So both we are taking together. Means the card drawn is an ace of ace, means it shows a letter A of spades. So A of spade in the sense P of E intersection the event, we can say that P of E intersection F. P of E intersection F is equal to, there is only one A in the spades. So only one chance, that is 1 divided by total number of outcomes, there is 52. So once again, E and F is an event. E and F together, okay? E and F is the event. The card drawn is the ace of spades. Means there is only one A among spades. So 1 divided by total number of outcomes, that is 52. Then P of E given F, let's calculate. P of E given F is equal to P of E intersection F by P of F. That is a formula. Then let's substitute it. That is 1 by 52 is P of E intersection F divided by P of F is 1 by 13. So here denominator will go to the numerator. So 13 by 52 will come. 13 by 52 when we cancel, we will get as 1 by 4. Here P of E is equal to 1 by 4 that we have calculated before. P of E is 1 by 4 and P of E given F also 1 by 4. So both the probabilities we are getting same. Means we can conclude that occurrence of event F has not affected the probability of the occurrence of the event E. Means probability of E alone, if we calculate directly, if we calculate, we are getting 1 by 4. And P of E given F also we have got 1 by 4. P of E given F in the sense the probability of occurrence of event E after the occurrence of F. Probability of event E after the occurrence of the event F. Means after F is happening also, probability of E is same as 1 by 4. Means both the probabilities are same. We can conclude that occurrence of event F here, E given F means it is a condition. Probability of occurrence of E after the occurrence of F. So occurrence of the event F has not affected the probability of occurrence of the event E, because both the probabilities we have got as 1 by 4. This is our conclusion from here. Again, P of F intersection E we can calculate. P of F intersection E equal to, formula when we write P of E intersection F. F intersection E and E intersection F both are same, divided by P of E. So P of E intersection F we have calculated here, that is 1 by 2 divided by P of E is 1 by 4. So here P of E is 1 by 4 we have got. Then as before, cancellation calculation we can do, that is for denominator will go to the numerator. So 4 by 52 when we cancel, we will get as 1 by 13. This 1 by 13 is our P of F. So we can come to the conclusion P of F is equal to 1 by 13 and P of F given E also 1 by 13. So here, like the previous one, we can come to the conclusion. So the occurrence of the event E is not affected the occurrence of event F. So that is what the conclusion shows, that the occurrence of event E has not affected the probability of occurrence of the event F, because probability of F, if you directly calculate also, we are getting 1 by 13, and after the occurrence of E, if you calculate the probability of F also, we are getting 1 by 3. Means the occurrence of event E has not affected the probability of occurrence of event F. Then by observing these two conclusions, we can come to the final conclusion that E and F are two events such that the probability of occurrence of one of them is not affected by the occurrence of the other. E and F are two events such that the probability of occurrence of one of them is not affected the occurrence of the other. Such events are called independent events. Means occurrence of one is not affecting the occurrence of other. Means they are independent. As the word says, independent means not dependent. They are not depending each other. So this is the condition for independent events. E and F are two events such that the probability of occurrence of one event is not affected the occurrence of the other. See some important results related to independent events. If E and F are independent, then P of E intersection F is equal to P of E into P of F. P of E given F is equal to P of E, and P of F given E is equal to P of F. So these three are important results, so you have to keep it in mind. E and F are independent means this condition must satisfy, that is P of E intersection F is equal to P of E into P of F. And two more results, P of E given F is equal to P of E, that means here the numerator, because here the previous example it was clear for you, the occurrence of F is not affected the occurrence of E, means P of E given F is P of E itself. And here also same thing, P of F given E means the occurrence of E is not affected the occurrence of F. So P of F given E is also P of F, provided P of F and P of E must not be equal to 0. Move on to the exercise questions. First question from exercise 13.2. If P of A is equal to 3 by 5 and P of B is equal to 1 by 5, find P of A intersection B if A and B are independent events. So, conditions are given to you, values are given to us. P of A is 3 by 5, P of B is 1 by 5. We are asked to find out P of A intersection B given that A and B are independent events. We have learned the result. If A and B are independent means P of A intersection B is P of A into P of B. So P of A is given to us, P of B is also there. So let's substitute it. That is P of A is 3 by 5 and P of B is 1 by 5. So 3 by 5 into 1 by 5, that is equal to 3 by 25. That is the answer. So here you must note the result. If A and B are independent events, P of A intersection B is P of A into P of B. Just direct substitution, you will get the answer. Question number 2. Two cards are drawn at random and without replacement from a pack of 52 playing cards. Find the probability that both the cards are black. Two cards are drawn at random and without replacement from a pack of 52 playing cards. Without replacement in the sense, once you have taken the card, it is not replaced. Means out of 52, if you have taken one card, the next time the total number of cards will reduce to 51. Because one you have taken and you have not replaced. That is the meaning of the word without replacement. Find the probability that both the cards are black. Since there are 26 black cards in a deck of 52 cards, there are 26 black and 26 red cards are there in a deck of cards. So it is mentioning about the black cards. So we have to think of the number of black cards. That is 26 black cards in a deck of 52 cards. The probability of both cards drawn are black is equal to probability of first card drawn is black into probability of the second card is black if first is black. Here P of A into P of B, that is a formula we have to use, means both are independent. That through an example we have already discussed this matter. So probability of both the cards drawn are black is probability of first card drawn is black into probability of second card is black provided the first is black. So first card black means we have 26 black cards. Out of 26, total number of cards 52. So 26 divided by 52, that is the first probability, into probability of second card is black if first is black. First black card you have already taken and kept it aside and you did not replace it. So 26 number will reduce to 25 because one black card you have already taken, and the total number of cards also 1 will reduce because out of 52 one black card you have taken. So only 51 balance. So next probability will be 25 divided by 51. One card is reduced. That is what it says without replacement. So this is the probability. Go for a little bit of calculation. So we will get the answer as 26 and 52. When you cancel, you will get as 1 and 1 by 2. So 1 by 2 into 25 by 51. No cancellation is done here. Then the final answer will come as 1 into 25 is 25 divided by 2 into 51 is 102. So 25 by 102 is the required probability. Next, move on to question number 3. A box of oranges is inspected by examining 3 randomly selected oranges drawn without replacement. If all the 3 oranges are good, the box is approved for sale otherwise it is rejected. Find the probability that a box containing 15 oranges, out of which 12 are good and 3 are bad ones, will be approved for sale. So this is a practical question. A box of oranges is inspected by examining 3 randomly selected oranges. In a box there are oranges, and from there 3 oranges randomly they are choosing without replacement. It means once an orange is taken and it will not be replaced. If all the 3 oranges were good, then only the box is approved for sale. So from a box of oranges, they are choosing 3 oranges at random and without replacement, means whatever they are taking, they are not keeping it back. And if all the 3 oranges are good, then only they will approve that particular box for sale. Otherwise, it will be rejected. Find the probability that a box containing 15 oranges, out of which 12 are good and 3 are bad ones, will be approved for sale. You can see here, if 3 oranges continuously, if they feels good, then only that box will be approved for sale. But here in the box, total 15 oranges are there, out of which 12 are good and 3 bad one also there inside. So we have to find out the probability that a box containing 15 oranges, this box will be approved for sale. That is what the question. We have to find out the probability. So let's write down the number of things which is given to us. Number of oranges in the box, total 15 oranges are there, and a number of good oranges 12 are there, and a number of bad oranges 3. And if any one of these 3 comes out, then the box will be rejected. And if these 3 is not coming, out of these 12, if any 3 comes, then they will be approved for sale. So here, let A, B and C be the respective events that the first, second and the third drawn orange is good. So here 3 events, A, B and C, because they are taking 3 oranges randomly. So A, B and C are the events. Probability that the first drawn orange is good is P of A, because whatever oranges they are taking, it must be good, then only it will be approved for sale. So probability that the first drawn orange is good is, we have 12 good oranges, okay, then these 3 is bad ones. So out of this 12 only 1 should come. So 12 divided by 15. This is the probability. Then probability of getting second orange good one is P of B, that is equal to first good orange you have already taken. Out of 12, 1 you have already taken. That means you will be having 11 balance, 11 good oranges. Out of 11 out of 14, because total number of oranges 15, from there you have taken 1 good one, so total also reduced to 1, good one also reduced 1, so 11 divided by 14. Next is probability of getting third orange good, that is P of C is equal to, already you have taken 2 oranges, first good one you have taken and second one also good one you have taken, and 2 numbers reduced, means out of 12 now we are having 10 good ones. So 10 divided by, out of 15 total number of oranges we have taken 2 and not replaced, so we are having 13 balance. So 10 divided by 13. Here independent events, since the box is approved for sale, if all 3 oranges are good, that means probability of getting all the oranges good is equal to 12 by 15 into 11 by 14 into 10 by 13. This is the probability. So when you multiply it, or when you do the calculation, you will get as 44 divided by 91. So the probability that the box is approved for sale is 44 divided by 91. This calculation you must do it in a rough sheet of paper. Please do not copy the answer. So 44 divided by 91 is the required probability. Dear students, today we have discussed the multiplication theorem of probability and the concept of independent events. Hope it was clear for you all. I request all the students to go through the exercise questions and solve these problems independently. And while solving, if you have any doubt, please note it and keep. We will discuss it during the discussion session. Thank you for watching.